This lesson is about confidence intervals for means. To understand what that is, let's consider this situation. We want to know the average college graduate IQ. We call this population parameter mu, meaning the population average. And ultimately, a confidence interval is a statement like this, a statement that mu is between something and something. And filling in those blanks is essentially completing the confidence interval. So we randomly select 40 college graduates. We give each one of them an IQ test. Here are the results. It turns out the average among this sample is 113, which you could find yourself by simply adding them all up and dividing by 40. We call that our sample average, symbolically known as X bar. We also call this our point estimate in this context because in our quest to give a interval of values for mu, this one point on a number line, this 113, is the best single number or single point that we have to represent mu. That doesn't mean that the population average will be 113 just because the sample average was, because samples vary. But if we had to pick one point to estimate it, this would be the best one, and hence the name point estimate. Now suppose we wanted to make this statement with 80% confidence. That means I want to design a procedure where my sample average will end up estimating mu correctly 80% of the time. To do this, we need three things. We need something called a standard error, something called a critical value for z, and something called a margin of error. And let's go through how to get each one of those. First, standard error. A standard error is, in some sense, a measurement of how far off my point estimate is from my actual population average. In other words, the standard error gives me a sense of how far X bar may be away from mu. Now, to compute the standard error, I would need to know something about individual variations among college graduate IQs. In other words, I would need to know the standard deviation of college graduate IQs. Suppose it's assumed that the population for which we are trying to estimate mu has a standard deviation of 15. How would we know the standard deviation of a population without knowing each individual member's IQ? Well, we couldn't technically know it, but there are statistical situations in which it's safe to make certain assumptions, and let's assume for the case in this problem that we are making that assumption, that we know the standard deviation is 15. By the way, this kind of problem, where we assume to know the population standard deviation, is called a sigma known problem, traditionally, because we're making the assumption that we know sigma for the entire population for which we're estimating mu. This is not always the case, but it is in this particular problem, let's say. So now, to get standard error, it turns out you have to divide the population standard deviation by the square root of your sample size. This is something statisticians have figured out, and we'll leave it to their expertise and assume that that's a great strategy, which it is. In general, we could say, here's a formula for standard error. Going back to this particular case, this standard error works out to be about 2.37. And just to give you a sense of what that means, it means that my estimate of 113 which is the only estimate I have so far for the population mean, may be off, and it wouldn't be unusual for that point estimate to be off by 2.37. Now on to critical value. To compute the critical value, there's a formula that's in most calculators and most software applications. It's called the inverse norm formula. And essentially, to get your critical value, you plug in the confidence for C, which in this case is 80%, and you work that out, which works out to 1.28. Now, from a calculation standpoint, that's it. We have our critical z-value, end of story. But it's helpful to have a broader understanding of what this actually means. What does it mean to say, what does the 1.28 mean? The meaning of that is that in order to make an 80% confidence interval, my point estimate can be off by as far as 1.28 standard errors. And to give you a broader sense of what all of this represents, imagine the following. An 80% confidence interval means that I'm designing a process which will capture the correct population average 80% of the time and be wrong the other 20% of the time. Well, in order to do that, I need to know how many standard errors away 80% is in the center of a bell curve. But to know this is the same as to say I need the z-score or the z-critical value here. You'll recall that z is the number of standard deviations or standard errors away from the center. And to compute z, most software and calculator applications use what's called the area to the left model, meaning I need to enter the area to the left of this black arrow. But of course that area is 90%, 80 plus 10. And that's where the 90% came from in my inverse norm function. And if you'd rather think of it that way than to use the formula, you can. Either which way, I now have my critical value of 1.28. So on to margin of error. The margin of error in this case is going to be 1.28 times 2.37, or more generally, my critical value times my standard error. And this makes sense when you think about it. If I'm allowing myself to be 1.28 standard errors off to be 80% confident, and each standard error is 2.37, then it makes sense that I would multiply these to get a margin of error, which I will round to 3. So, I now have my margin of error. Let's analyze what that means. Remember our original point estimate of 113? That number which, if I had to pick one number to estimate the population average, I would choose my sample average as my best estimate. Well, the 80% confidence margin of error tells me that that 1.13 could be off by as much as 3 points, meaning that the true population average could be 3 higher than that, or it could be as far down as 3 below that. And these two numbers in red are the lower and upper limits of my confidence interval. So, as my final statement, with a confidence level of 80%, I can state that the average college graduate IQ is somewhere between 110 and 116. By the way, I looked it up just out of curiosity, and it turns out that the average college graduate IQ is 115, which did, as it turns out, fall in our confidence interval. And that completes the lesson.